Moving on to our next session, non-terrestrial quantum communication and its impact on cybersecurity. I would like to invite Ms. Anindita Bannerjee, scientist with CDAC. Dr. Anindita is a PhD from JP Institute of Information Technology. She has published papers in more than 20 journals. She has co-authored a book on optical quantum computation and quantum communication, published in SPIE Spotlight series. She's worked as quantum research head and VP at Q New Labs Private Limited, focusing on quantum safe solutions for cybersecurity. She's played a key role in developing India's first quantum technology product in quantum key distribution and quantum random number generator in 2021. I welcome you on stage, Dr. Anindita Bannerjee, please.
Good afternoon. So I'll be talking about quantum communication and how does it address the threat on cybersecurity. So I'll begin with the quantum technologies we are pursuing in CDAC, and thereafter we'll talk about the threats of cybersecurity from classical as well as quantum perspective. Then I'll talk about the quantum rules of security, how we can leverage the advantages and help the entire crypto system become more robust towards the advancement of classical technology as well as the threat which quantum gives. Then we talk about the different types of quantum key distribution. I'll be particularly talking about non-terrestrial part, and then we'll look at the global developments in this area. So we begin with quantum technologies at CDAC. So we work on quantum computing as well as communication. You will have communication inside a quantum computer, and you'll have a quantum computing which will be used eventually for a quantum communication network. So they both go together. So in computing part, we are working on certain hardware for quantum processors, which are in a very beginning stage. We are working on how to accelerate the performance of quantum simulators. Then we are working on hybrid quantum classical use cases. We are talking about how to develop a quantum data center in India, which will have HPC and QC integrated and perform hybrid application. And then, of course, quantum education is one of the very important area. We need to build quantum workforce, and we have taken certain initiatives in that direction. My strong area is in quantum communication, and there is already an existing network between IIT Madras and CETS in Chennai, where they have developed a quantum key distribution system. Now, the second project is on drone quantum communication, where we are planning to put a quantum communication systems on aerial platforms, fly it to a height of about, say, 500 meters, and see how they perform the communication. Now, the next stage would be a satellite communication, and before one stage, I say it will be ground-to-ground, terrestrial-based communication. Then we are also building terrestrial QKD devices for financial areas. I won't spend much of a time. I have got a very limited time. So if you have any questions, I'll be happy to take them after the session. So Dr. Venkat from IBM has very nicely addressed that all your passwords, all the secrets, national, international, your credit cards are, are based on the hardness of a mathematical problem. Okay. Now that mathematical problem will take billions of years to be broken, and we call them safe. If you look at the history of cryptography, there have been certain cryptographic algorithms which are safe for 100 years, but after that, when a new technology comes, it breaks. So we are in that age because the mathematical problems which are there safeguarding your passwords can be solved in a quantum computer in polynomial time, means few seconds, billions of years to few seconds. Now this analysis has been well published in the research articles, and I think IBM will bang on with me, and he will say that with the advancements of the quantum computing hardware, This can be done even faster, maybe 20 to 25 years, which I'll show you in my presentation. And then, of course, there are advanced computing techniques and computing hardwares. We have vulnerabilities of the physical link. You can always tap on a fiber channel, and your information can be leaked from there. The mathematical algorithms will have backdoors. So you have innumerable, problems. See, this technology is 70 years old as a classical computer. And you keep on putting security patches to it. But the problem which you are going to face from the coming of a quantum computer will not be, you will not be able to solve it using any security patch, but you'll have to move to quantum technology, okay? Then from quantum, so as Dr. Venkat had rightly pointed out, we are able to solve some of the mathematical problems, not all, but some. But they are important because it is associated with security. Then second is quantum hackers. Again, you must have seen in the IBM's presentation that quantum solves certain areas, like it uses quantum assisted AI to go for fraud detection analysis. So when you have a fault tolerant quantum computer, they will be not only breaking this particular algorithm, but also the capability will rise to such an extent, the cryptanalysis, that even the conventional classical cryptography will not be safe in that area. Now we go for the cybersecurity in the area of quantum computing. Now this is called Moscas inequality. We say that there has to be a migration time. What is it? It is a number of years needed to transition to quantum safe solution. Then we have shelf life, the life of the secret. Then we have threat, which means the number of years before the relevant threat actors will be able to break the vulnerable cryptographic systems. The idea is shelf life plus migration, if it is greater than threat, and mind you, this is a very, very important statement, and this has been running globally, because this is a threat if we do not react on time and we are already late, okay? So the quantum computer, if you can look at the graph, it has been taken from the quantum threat timelines by Michel Mosca. So a lot of advanced studies are happening on the predictions based on market surveys and actually talking to scientists. And it has been predicted by 25 to 30 years, you will be having a crypto cracking quantum machine. And that is the reason, see, many things doesn't come in public knowledge, right? So when we are investigating certain technologies deep, so there is reasons, full valid reasons to believe in this. So we go on to the next part. What are the quantum rules for security? Why we should be interested? Though what is ideal? What is the best? The best is the encryption keys. That should not be copied, okay? So the security is as good as the encryption key. The World War II, why did it break? Because they were using one-time password and they used the keys twice. So the security is as good as the encryption keys. Now this is very important for cybersecurity, right? Encryption keys. Now encryption keys should not be copied. Today we use trusted couriers. You must have seen, guards with suitcases. They carry the keys from this one place to the other. This is how it is being taken from one point to the other. But this is, you have no guarantee. Somebody can always copy it and put it back. It is not as simple as I speak, but this is a challenge. And that is why we have most of the interest coming from strategic agencies. So the keys should not be copied. Keys should be random. And key tampering, if somebody is monitoring your key, if somebody is copying your encryption key, that should be detectable. These are important again, because today internet, we are using public key infrastructure, okay, asymmetric cryptography. And that is very well threatened by Shor's algorithm. So all these can be addressed by quantum key distribution. The only simple sentence you remember, it solves the problem of generating symmetric encryption keys. That is all what quantum communication does. It is as simple as that. So we move to the next, what are the rules? Now, of course, quantum physics has different rules than classical physics. You always encode information on a physical system, and that physical system follows the classical rules. When I'm talking about the system, it follows the quantum rules. Now, they too are a little counterintuitive, but that is very simple once you have a touch and feel about the subject. So they behave differently, fine. In that world, you're not able to copy a quantum state. And that can be proven mathematically. And if you visit a quantum lab, you'll be doing experiments where you can actually investigate the matter. So you cannot copy the information. Any perturbation you do to that fragile state, one particle of light, it is in power of, say, some picowatts. So if you monitor that fragile state, it's going to be disturbed, your information is going to be tampered, and you'll be able to detect an enemy. Now, all this I'm talking about has actually happened and has happened in India. Okay? There are 3 to 4 organizations working on this quantum technology hardware devices. And it calls for a state-of-art engineering. Then only we can achieve it, not with a noisy system. Then we have superposition, Banner inequality. It's mathematically proven to be secure, unlike classical. Then we have, it ensures what I just said, secure symmetric keys are generated. Just remember, classical, you are generating a key and distributing in PKI. What we are doing, we are generating simultaneously secure encryption keys under the nose of an eavesdropper. Ekdam samne we are generating, and we are challenging that if you can perturb it, because we are going to find it. It's all done mathematically. So this is how it works. So we have 2 ways of going about it. The 2 ways can be pursued separately. One which US is doing, with a lot of noise. They are working on post-quantum cryptography, and they have asked actually all the crypto systems to be transitioned to be made quantum safe. So they are actually working on that Moscow's inequality, right? Then we have quantum encryptor. Again, so it's a point-to-point. It's of 3 types: fiber-based, terrestrial, non-terrestrial. Means entire system is on air. Then we have satellite QKD. You have a ground station, and then you have a satellite, or you have an inter-satellite. I will tell you about the developments in Europe which are actually working on satellite QKD to ensure futuristic cybersecurity, systems. So it is actually happening, and a lot of money is being pumped in. Going back, this is something, so this is very simple. Like, you have a message, you have an encryption algorithm, you put in the encryption key, you send the cryptogram, you have a decryption algorithm, then you have a decryption key there, and then you get the message back. So according to, the best thing is the adversary should know everything about your system. Even the device you're working on, they can have the same system. The algorithm you're working on, they have the same knowledge. But only your encryption key should be yours. So that is the critical part. And we are solving that problem in the classical world using quantum. So here again, you talk about key distribution. 2 types, prepare and measure, systems which QNU Labs, the first startup in India on quantum technology, is working on. Center for Development of Telecommunication, CDOT, they have developed a system we call it coherent one-way, prepare and measure protocol. Then IT Madras has developed it, IT Delhi has developed it, DRDO and many other organizations in India have actually developed the systems. Entanglement-based scheme. Now, maybe if you want to know about what is superposition, what is entanglement, I can brief you after the session. So we are working on entanglement-based systems, and these are 2 protocols. So whenever a protocol is discussed, it's the worldwide brainstorming by the scientists globally to identify the challenges, because it's all mathematical. So once they say, fine, your quantum adversary with quantum memory, with quantum weapons will not be able to crack it, then we move forward. We understand how much of information can be leaked if I'm applying the protocol. So whenever I'm doing this kind of a system, we do a lot of analysis, and we quantify the information leaked, and then we apply some hashing, and we get finite keys which can be used by other cryptographic systems. Now this is how the architecture looks like. There's a lot of physics, and there's a hell lot of maths, and there is a massive amount of classical engineering, state-of-art, precise, clean engineering which goes into it. Okay? So the physics parts comes only in the quantum data transfer. If I can use the light, yeah. So the quantum part is very small. It's challenging. It has to be very neat. It has to be handled with a lot of care, because it's a very fragile system. That is the only part, quantum. Rest, everything is classical. So there's a lot of opportunities for engineers here. There's a lot of opportunities for mathematicians here who can act, and a lot of opportunities for people to see how this can be applied in the real network. If you want me to delve on that, I can always discuss this again. So now quickly I'll take you to the quantum states which I'm talking about. So these are the quantum circuits. I think they were done in IBM. So this is quantum gates. So this is the state I'm talking about. Mathematically, I represent them in bars and kets. 0, 0, 1, 1, these are logical states, but they have a physical representation. We usually encode information. So I'll create a photon here. Okay, the photon has multiple degrees of freedom: polarization, orbital angular momentum, phase. I will encode some information on that photon, and that will travel. Photon is known as flying qubit. That will travel to the other party, and then I will do some measurement. I will decode the information. So this is how quantum communication happens. And this is the physical, the box you're seeing is a crystal, nonlinear crystal. So what happens is, let me tell you, suppose 50 million watt light is pumped in. Out of that, there is a chance of 1 in billion. That 1 in billion photon will actually release 2 daughter photons. And those are the states I have to take. Now imagine the challenge. How much I have to block, how much I have to maintain, because I'll be working on those 2 states. Okay. So then we come to the classical attacks, particularly denial of service, where person is actually listening to what you are sending to Alice. Why this happens? In your classical communication, you are encoding 0 or 1 to some 10 million photons. The adversary will tap, say, few million photons out and will be able to encode find the information. But we are working on 1 photon. So please remember that. So there, this, okay. So there, this kind of attack will not be tolerated. Then, of course, adversary is tapping in, altering the state, and again sending it back. For example, the encryption keys, right? So these are the tamperings which can happen in the classical world, but in the quantum world, I'll get an indication, and I will drop the encryption keys. I will not be using it. Moving forward, I won't spend much of the time here because it shows how the optical circuits are put to generate the quantum states, nothing more. This is the protocol. In the interest of time, I will skip it. It just tells you how the entire protocol works. What you should see is the information about the key is not transferred. What happens in cybersecurity classically? I'm generating the encryption keys, packing it up with an RSA algorithm and sending it across. What happens in quantum? We are not generating the key and sending it. We are generating 2 keys simultaneously at 2 different locations. So this is how we are different from the classical world, and there is nothing written that I'm transferring the keys. They are always generated spontaneously, and every time I do it, every time it will be different. So now the different QKDs, fiber QKD has been developed by CDOT, QNU Labs, Macan. Static free space QKD, this has been demonstrated by ISRO and by Physical Research Laboratory. Then this is the area which CDAC is working on, where we would want to generate the quantum states in air and then distribute it in the ground location with a distance of, say, about 300 meters. But even the small distance is a huge leap, if you are able to do it. Then we have satellite QKD, which is pursued by ISRO. So they have already built a module for space QKD, and hopefully by the end of this year or next year, you'll be able to hear about it. So things are happening in India, and we should be very proud and also try to encourage such developments and participate as well. Then we have, it's going back, yeah. So then we have wide drone. It has few merits. See, if you have drones in air, suppose it is a strategic requirement to distribute encryption keys for a cryptography. You have a difficult terrain, and there is a call. You cannot build ground stations and do satellite QKD. You cannot lay fiber and do fiber QKD. You'll have to go for such networks like a swarm of drones, which will distribute keys from one to the other. If one of it is shot down, the other can take its place. So what we are working on, it's agility and it's maneuverability, which we provide along with the existing technologies with ISRO and CDOT. Moving forward, yeah, this is the POC we would want to focus on, terrestrial free space, and thereafter we go with non-terrestrial key, and finally we do the entire QKD over drone. So this is a POC we would want to work on, and we are working with ISRO. We'll be working with ISRO as well as defense on these kind of demonstrations. So this is how the integrated quantum communication will look like maybe in 10 to 15 years of time. And so there you have terrestrial, you have non-terrestrial, and you have satellite. Now your 6G technology will be using, the security backbone of 6G is going to be quantum communication. So this is why it is interesting. Now this is the, the Chinese have actually built a fiber network of 4,600 kilometer using terrestrial as well as satellite QKD, satellite known as MISO. They have used and demonstrated, already demonstrated, please note. And a lot of standardizations are actually happening, starting with HC being the first one, and followed by the Joint Technical Committee by the European agencies, and we have ISO, and also recently Department of Telecommunication has also published standardization for quantum safe cryptography. So when India has published a requirement, a standardization document on quantum communication, means there is going to be a proliferation of startups, and there will be a requirement for industry adoption for quantum safe cryptography. And with the launch of National Quantum Mission, which has been cleared by the cabinet recently, this is going to be one of the priority areas. I'm finally coming to the end of this presentation. So this is a global landscape. These are the few works which has been done in India, in US and China in this area. And finally, this is the last slide. These are the organizations which have taken up space to earth quantum communication for cybersecurity. So you can go through these documents, European Quantum Communication Infrastructure, and if you look at the second point talks about quantum overarching system architecture concepts. They are used to ensure the European Union's capacity to cope with tomorrow's cybersecurity challenges. So this is on their agenda already. And then your other projects, which is here, I will not spend much of the time. I will be very happy to take questions after this session. Thank you.
Thank you so much, Dr. Anindita, for this very informative session. I would like to invite Mr. Parikshit Pandey, AVP Sales, Neosoft, to come on the stage and felicitate Dr. Anindita.